Right, then we'll start with the AVL trees. Uh, so AVL tree, let me just give you a brief introduction first, and then you can understand when we are trying to solve the problem in AVL tree. So AVL tree can be defined as a self-balancing binary search tree, or we can say this as like self-balancing BST. All right, and why exactly we need to balance the height of a tree is this. So in general, in binary search tree or say a BST, the time complexity in worst case is big O of n. So what exactly this big O of n is? So if you take a tree of this particular structure, right? So let us say we have a binary tree like this. So wherein we have values like this. Okay. So if this is how the tree is, then the balance factor or the height of the tree is not actually equally balanced. So in this case, if you would like to search 3, right? So if someone is asking you to search 3, so the number of comparisons that we are going to make here is 3. So for example, first we will search with this root node, and then since 3 is smaller than 10, we are going to go check with 5. And since 3 is smaller than 5, we have to again make comparison here, and this is where we will say that the element 3 is found, right? So here the number of comparisons that we have taken is 3, and whereas the height of the tree is also 3. All right. So in worst case scenarios, the search time complexity for binary search tree is big O of n, which is like maximum. So for example, imagine we have numbers in descending order, which are stored in a binary search tree, like say 10, 5, 3. And if you keep going like this, right, and if you keep going like this, so -5, something like this. So if someone is asking you to search for -5 now, the number of comparisons that you are going to make is very, very high. And if you imagine this for say 1000 numbers, where the binary search tree is constructed like this, in that situations, the time complexity is going to be very, very high. So which is not the feasible option for us to go with. So to get rid of this problem, we are going to come up with some solution, and that solution is balancing the height. Balancing height. So how do we balance a height is some important question. So to balance the height of a tree, so for example, let us say the previous example that I've taken. So we have 10, 5 and 3. So if you balance the height of a tree into this, so here if you try and search 3, so how many number of comparisons are we going to make here? We are going to make only 2 comparisons. So first we will search with 5 and then we'll search with 3. So here the number of comparisons were reduced by 1. So if you imagine a bigger tree and if you try balance the height of a tree, then the number of comparisons will be gradually reduced. So here the time consumed in a worst case situation in AVL tree or a balanced tree is big O of log n. So which we say the logarithmic time complexity. So it is always in algorithms is that, so the linear time, which we say big O of n, is always bigger than the logarithmic time, which is big O of log n. So our focus is to construct a binary search tree or construct a tree whose time complexity in worst case scenario is big O of log n. And this is the reason why we are going with AVL trees or different balancing trees. And among self-balancing trees, so we have something called AVL tree, and then we have different trees like red black tree, and also we have something called splay tree and B tree. Right? Now these are all the trees that we have which were said to be like self-balancing binary search trees, right? And this is why we are going to go with AVL trees. Hope you understood why we came up with AVL trees. AVL trees are self-balancing binary search trees which help in trying to get the time complexity in worst case scenarios into lesser time complexities. Like from big O of n to, we can get the time complexity into big O of log n, right? Hope you understood why we need AVL tree and why we have to balance the height of a tree. Hope you have understood the purpose of AVL tree. And if you have any questions, then you can ask me on this, and then we can move on to the next topics of AVL tree. Right. Good morning, everyone. Uh, Jeevan has joined. Right. Now we will discuss about balance factors or the properties in AVL tree. So in AVL tree, the important properties are this. So the balance factor. So this balance factor is something which tells us whether the height of a tree is balanced or not balanced. All right. So we will see what balance factor is and how you can compute the balance factor and all that. So it is to be said that in AVL tree, so the balance factor for any given node must be within the range of -1, 0 and +1. So this is the only allowed balance factors, and if for any given node, if the balance factors are not within this range, then we say that the height of a tree is not balanced, and we say that tree is not a valid AVL tree. And the next property that we are going to see is, so it has to satisfy, like AVL tree has to satisfy all the properties of binary search tree as well. It has to satisfy the all properties of binary search tree also. Okay. Now we will see how you can compute the balance factor. So the balance factor formula goes like this. So height of left subtree minus height of right subtree, right? So this is the formula for computing the balance factor for any given node in the tree. Okay. So I believe you already have an idea what height is. So height of a node can be found like this. So the distance or the number of edges between that node to deepest child node. Okay. So for any given node, the height can be said like this. So the number of edges between that node and the deepest child node. All right. So the number of edges between that node and the deepest child node is called as height of a node. So for example, if you take this particular tree, so let us say we have a tree like this. Okay. And let me just fill some values here. So let us say I have 5, 2 and 1. So here if you want to calculate the balance factor for this given node, okay. So the height of left subtree, for example, the height of this particular node in left side is, so the deepest child node is this particular node for 5. And for this deepest child, so the number of edges that we have is 2. So we have 1 here and then here 2. So it is 2 in the left side, and whereas in the right side we don't have any nodes, so it is going to be 0. So now the balance factor for this node will be 2, and whereas for this particular node it is going to be 1. So why 1? Because so in the left side we have one edge to the deepest child node, which is 1, and in right side we don't have any nodes, and that is why it is 0. So it is 1 minus 0, then we end up with 1. And for this particular node we don't have any left child or right child, then the balance factor will be 0. So this is how you compute the balance factor for any given node. So can anyone tell me now the balance factors for this particular node? So let us say here I have 10, and here I have 5, sorry 8, here I have 9, and here I have 5. So can anyone tell me the balance factor for this particular node now? So what is the balance factor for 10? You can mention your answers in the comment section. So Harshavardhan is telling the balance factor for 10 is 3000. It is not 3000, Harshavardhan. Any other answers? So balance factor for 10. Alright, so Dinesh is telling us the balance factor for 10 is 2, and Hassan is telling 3. Alright, so great. So now we will see the balance factor for 10. So yes, the balance factor for 10 is 2. We will understand why it is 2. Alright. So the balance factor for 10 is computed as 2 because, so in left subtree, the deepest child nodes are this 5 and 9. So here the number of edges between the deepest child node and this particular node is 2. So that is what is 2 minus, and right subtree we don't have any nodes or child nodes. So we are going to take as 0. So 2 minus 0 becomes 2. And whereas for this particular node, so it is going to be 1 in the left side and 1 in the right side. So it is 0. And here the leaf nodes will always have the balance factors of zeros. Right? Awesome. Great. I believe you have understood how you can compute the balance factors. Right. Since you have understood how you can compute the balance factors, now we will see how we can perform the very first operation, or insert operation. Or before we get into insert operation, let us see how you can balance the height of a tree if the balance factor is not within the range, allowed range. So how you can do that is using rotations. Okay. So the rotations are the operations that we make use in AVL tree to balance the height of a tree. So for example, in this case, so let me take this tree. Right. So let us say we have a tree like this. Maybe some numbers will do, 9, 8, 7. Right. So here if you compute the balance factors, the balance factors would look something like this. So 2 for this and 1 for this and 0 for this. So here if you see, the balance factor for this given node is not within the range of -1, 0 or +1. So here we have to perform a rotation operation to get the balance factor again within this range. So here what we are going to perform is, we are going to perform something called a right rotation. Here we have to perform something called right rotation. So why right rotation? Because if you see, so the balance factor is a positive value, and if it is positive value, one thing that you could understand is that, so in the right side we don't have any nodes which will balance this particular height. And so what we should do, we should try and push some nodes to the right side. So here what happens is, the middlemost value can be pushed into the parent position, and this parent becomes the right child, and this left child can be a left child as it is. So after performing the right rotation, the tree would change into something like this. Right. So here if you compute the balance factors now, for leaf nodes it is going to be 0, and for this node it is going to be 1 in the left side and 1 in the right side, so it is going to be 0. So now if we compute the balance factors are within the allowed range, which is -1 to +1. So now we say that this is a valid AVL tree, right? Now let me give one exercise for you and tell me what should we do in this case, right? Okay. Now can anyone tell me what operation should we perform in this case? So you can try and relate this to this particular rotation and tell me what rotation should we perform here. Tarun is asking a question. Sir, for balancing we have to consider levels if we have only one right child for last node. So it is not about the levels, Tarun. To be honest, the balancing is done according to the height. So some would, tell that height is nothing but number of levels, but I understand height in terms of number of edges. So for example, here if you take, so here in this example, or let us say in this example, so we have for 8, we have left child, there is the deepest child is 7, and the number of edges between this deepest child and this root node is 1, and so I take as 1, right? And minus the height of right subtree. So for 8 in the right subtree, the deepest child node is 9, the number of edges between them is 1, so 1 minus 1 will become 0. That is how you calculate balance factors. All right, it is not about the levels, so it is about the deepest child node, right? Do not worry, we will come across many different trees and you will understand balance factors very easily. So we are going to perform left rotation. Awesome. So as you have told me that I have to consider now something called left rotation. So because why we consider left rotation is this: first we have to compute the balance factors. So for the child nodes also, relief nodes, always it is going to be 0, and for 20 it is going to be 0 in left side, but in right side there is one node. So the deepest child node is 30 and there is only one edge between them, so it is going to be minus 1. So 0 minus 1, which is going to be minus 1, and for this it is nothing in the left side, so it is going to be 0 minus, and there are two edges, or two edges between the deepest child node, which is 30. So it is going to be 0 minus 2, then we end up with minus 2. Since we have a negative balance factor and we don't have, like, we have more nodes in the right side, like right subtree, so we have to push some nodes into the left side, and that is why we call this as left rotation. And the updated tree would look something like this. So here in this case 20 becomes our root node, 10 is pushed to the right, and 30 stays as it is in the right side, 10 goes to the left side. Now if you calculate the balance factors, it is going to be 0 for this because it is 1 minus 1, and for the leaf nodes it is always going to be zeros. Now we will see how we can perform a combinational rotations. All right, so the combinational rotations, there are two in AVL trees. So one is RL rotation. Okay, so in RL rotation, it is going to be like this. First, we are going to perform a right rotation, and then we are going to perform something called a left rotation, right? So for example, if you have tree like this, let me take an example. If you have a tree like this, okay, okay. So here if you see, we have a situation where the new node, or 25, is inserted and in the right subtree of 20 and as a left child. So here we have to perform something called RL rotation, or right left rotation we call this. So first we are going to perform right rotation between grandparent and parent, and then we are going to perform something called left rotation. So this is why we call this as right left rotation, and right left rotation is performed in this situation where you have inserted a right child in the left subtree, and because of which the balance factor was impacted. Okay, So here if you see, after we insert 25, the balance factor for 20 has the balance factors. So 0 for leaf node and 1 for 30 and 2 or minus 2 for 20. So since for this node the balance factor is not valid or not in the valid range, so here we have to perform something called right left rotation. Always do remember, in right left rotation the first rotation is performed between the grandparent, sorry, the not the grandparent, my apologies. So the first rotation is performed, which is right rotation. So the right rotation is performed between child node and parent node. Okay, and our agenda in this right rotation is, so we have to get all the nodes in this particular structure, all the nodes to the in this structure, and then we are going to perform something called a left rotation, and left rotation is performed between parent and grandparent. Okay, so after we perform the rotation between parent and grandparent, the tree is going to look something like this in this particular cap structure. Right, now let us see how we can perform this. So here what would happen is, first we have to perform a right rotation and then we should perform the left rotation. So the tree would change into something like this. 20 stays as it is because we are not performing any rotation on it. And here first we have to perform rotation between the child node and the parent. So child node is 25 and the parent node is 30. So after we perform the right rotation, 25 is pushed up and 30 is pushed down. Right, now this is in this particular structure, how I told you that should be in. Right, now we should not calculate the balance factors immediately. We should calculate balance factors only after completely performing both right rotation and left rotation. So here what happens is, now we have to perform a left rotation, which is final rotation in left or right left rotation. So here between 20 and 25 the rotation is performed. So the tree is going to get into something like this. 25 goes up, 20 is pushed down, and 30 stays as it is in the same place. Now the balance factors are within the range for all the nodes. So this is how you perform a right left rotation. Right, Gayatri is asking a question. We have more than node, we have node, have we can, okay, so I believe you're asking how we can perform rotation if we have more number of nodes. Do not worry, Gayatri, I will explain this AVL tree construction and different operations with a bigger problem, so that we'll have more number of nodes and you will understand how we can perform rotations if we have more number of nodes. My focus is to make you all understand these basic rotations first and then get to the bigger problem, right? I believe you all have understood right left rotation, and right left rotation is performed only when the imbalance happen because of a left child for the right subtree inserted. So here RL rotation is performed when the tree is in this structure, in this structure which is greater than structure. Okay, do remember this. Now we will see how we can perform a LR rotation or left right rotation. Okay, so just opposite to the RL rotation, LR rotation work. So here first we have to perform a left rotation and then we should perform right rotation. Okay, so our focus is to get the tree into this structure after performing left rotation, which is this structure. And after performing or getting into this structure, we are going to get the tree into this structure after performing right rotation. So we will see an example for this left right rotation, right? So let us say we have tree like this. Okay, so here if you see, the balance factor for this is 2 and for this it is -1 and for this it is 0. So here the imbalance happened after inserting 15 into the tree, and now what we should do is we should try getting this into within the allowed balance factor range. So here the child node is inserted in this position, so which is in the left subtree as right child. So when the imbalance happened because of the node inserted at this position and the tree is looking something like this, in this situation we are going to perform something called left right rotation, right? So first what we do is we will perform a left rotation between 15 and 10, which is child node and the parent node. So the tree would change into something like this. We will have 20 there, 15 is pushed up and 10 is pushed down. Okay, and now the last rotation should be performed between this 15 and 20, which is the parent node and the grandparent node. Now the tree would change into something like this. So this is how we perform a LR rotation or left right rotation. Now the balance factors are zeros for all the nodes. I hope you have understood how we perform different rotations. These rotations are very important to understand AVL tree. uh, do understand this, and if you have any doubts in them, please ask the questions so that I can answer them. So this is right rotation and this is left rotation. So right rotation is performed when the new node is inserted in the as the left child to the left subtree and it is pushed to the right side, and left rotation is performed when a new node is inserted as right child to the right subtree. Okay, and the combinational rotations are this, which is RL rotation, which we call as right left rotation, and when the new node is inserted as right child for the left child to the right subtree, that is where we use RL rotation, and LR rotation is used in this situation where the new node is inserted as right child to the left subtree. Okay, any questions on this, guys? If you have any questions, I'll clarify them, and then we can see a problem, how we can perform a insertion operation or how we can construct a AVL tree. Any questions? So if you have any questions, you can ask the questions so we can clarify them and then we can dive into a problem. So the question that was asked to me is to construct an AVL tree for this particular problem. Where is the problem? So what is the advantage of AVL tree compared to binary tree? Right. So the advantage of AVL tree is this. So as I said already, so in binary search tree, the time complexity is this, which is big O of n. So which we also call it as linear time. Okay, which we also call that as linear time. So for example, if you have tree like this, okay, so I'll just take some random numbers here, 10, 5, 3 and 2, and then maybe 20 here. Okay, so here if you see, the number of comparisons that we are going to take is very high. For example, if I am asking to search 2, so how many comparisons are we going to perform here? If you just see according to the binary search tree, first comparison is performed here between 2 and 10. So 2 is less than 10, so we're going to go to the left child, and again we have to make a comparison here between 2 and 5, and again here to make a comparison which is 2 and 3, and again 2 is smaller, so we are going to go to the left child, so which is 2. So here if you see, to search for 2, we have made use of something called 4 comparisons. So the number of comparisons that we have used is 4. So let us say we have converted this into AVL tree now. So after you convert this into AVL tree, the tree would look something like this. The tree structure is going to get changed into something like this. So here if you see, the number of comparisons that we are going to take is only 3. Okay, so if you see, so first we'll compare with 2 and 10, and then the comparison is made between 2 and 3, and then between 2 and 2. Okay, so here if you see, the number of comparisons that we have taken is only 3. So here it is a very small tree, so the number of comparisons are not that very different. It is only 1. But imagine a bigger tree wherein you have like 1000 numbers or 2000 numbers, then this time complexity would definitely make an impact in the execution time of your program. So our goal in writing algorithms or programs is that the search time should always be as low as possible. And the known fact is that linear time complexity, which is big O of n, is always bigger than the logarithmic time, which is log n. Okay, and the time complexity of AVL tree is big O of log n. So since the AVL tree is reducing the time complexity in search operations, that is why we are going to go with AVL tree than binary search tree if your program's goal is to reduce the search time. Right, so this is the benefit of AVL tree compared to binary search tree. I hope I have answered your question. No, it is just mentioned as Mr. BTech. I'm not sure the name is. Hope. Are there any other questions, or shall we continue with solving the problem in AVL tree? I'm just copying the problem which is asked by Asma in the comments actually. Uh, if you want me to solve any problems on any of the trees or any of the data structures, just you can ask me, so I can just uh, make a live sessions like this so that you can understand how you can solve them, right? I believe this is what the question asked by Asma, and I was asked to construct an AVL tree for this particular problem. All right, so we will go ahead and see how we can construct an AVL tree for this. All right, do remember, it is important to understand binary search tree because we are going to follow the binary search tree operations in AVL tree. All right, so first we will see how we can insert 3. We will see how we can insert 3. So since the tree is presently empty, I don't have to worry about the balance factors, or I don't have to make any comparisons. I can go ahead and make 3 as our root node. So 3 is inserted directly. But it is important to update balance factors for all the nodes after performing any operations in AVL tree. So here the balance factor for this node is 0 because we don't have anything in the left subtree or anything in the right subtree. Now we will insert the next number, so which is 2. Okay, so now to insert 2, so as there is a node already in the tree, I have to first make comparison. So first comparison is made between the root node and the new element which has to be inserted. So here 2 and 3 are compared. So after comparing 2 and 3, 2 is smaller than 3 and the left child of 3 is null, which is there is no node in the left child. So I can insert 2 directly in the left child as the left child. And as the insertion operation completed, now we have to calculate the balance factor. So balance factor for leaf node, it is always 0, and balance factor for this node changes now. So in the left subtree, we have one child node, and that is the deepest leaf child. So the height is going to be 1. So 1 minus, and the right subtree there is no nodes, so it is going to be 0. So the final balance factor for this node, it is going to be 1. And the balance factor that is allowed, we all know already, it is -1, 0 and +1. So it is -1, 0 and +1. So this is the allowed range. Now the balance factor of all the nodes are within the range of -1 to +1 or 0. So this tree is valid. So I can go ahead and insert the present tree like this. And to insert one, I have to make comparisons again. So one is compared with 3 and one is smaller than 3. So I have to insert one in the left subtree. But the left child of 3 is 2. So one present new value to be inserted with 1. And again, one is smaller than 2. So I have to insert 1 as the left child of them first. So the balance factor for leaf node is going to be 0. And for this node, it is going to be 1 minus 0. 1 because in the left subtree, there is one child node and that is the deepest child node. So it is 1. And in right subtree, I don't have any value. So it is going to be 1 minus 0. So we will end up with a balance factor of 1. And now we will try finding the balance factor for 3 here. So in the left subtree, the deepest child node for 3 is 1. So how many edges do we have here? 2. So it is going to be 2 minus, in right subtree I don't have any nodes, so it is going to be 0. So 2 minus 0, it is going to be 2. So now if you see, the balance factor for this node is affected. So here we have to perform a rotation operation in order to balance the height. Tell me, what rotation should I perform now? Okay, Uday is asking a question. The solving tree was in already descending order. Why the 5 goes to 3? I don't understand your question, Uday. So we have them in descending order. Not sure what the question is, Uday. Sir, can you construct an AVL tree for these numbers? Alright, Tarun, I'll construct AVL tree for that also, but let me complete this tree. This tree is not going to take so much time. And then we will construct an AVL tree for your given list of numbers also. Alright, I'm just taking a screenshot of your question so that I will not miss it. Can anyone tell me the rotation that is required in this situation? Any answers? So here we will be performing something called a right rotation, because we have inserted one as left child to the left subtree, and in this case we have to perform something called a right rotation. In right rotation, the middle node, which is the parent node, becomes the root node and the grandparent becomes right child and the left child stays as it is. So the tree would be updated into this. So 2 goes the root node, 3 is pushed down and 1 stays in the left child position as it is. Now if you calculate the balance factors, so leaf nodes will be 0 all the time, and for 2 it is going to be 1 minus 1, so which is going to be 0. So now the tree is balanced, and since the tree is balanced, so now we can go ahead and perform the next insertion operation. So the next node that we should insert is 4. So now we will see how we can insert 4. All right. Right. So the answers are correct. So been asked to shift them to the right side and we have performed the right rotation. Now we will see how we can insert 4, and to insert 4 we have to consider this tree as the present tree, right? And I believe everybody knows how binary search tree works, and now 4 is inserted at this position. And after inserting 4, now we should calculate the balance factors. So the balance factors are going to be this. So for leaf nodes, it is going to be 0. And what about this node? So it is left side, there are no any child nodes, so it is going to be 0. And in right side, we have one node, so it is going to be 1. So 0 minus 1, it is going to be minus 1. And whereas for 2, it is going to be 1 in the left side and 2 in the right side. So 1 minus 2. So the balance factor is minus 1. Now if you see, even though the tree is little right skewed, the balance factors are within the range of minus 1 to plus 1. So now we don't have to worry about balancing the height of a tree. So we can go ahead, perform the next insertion operation. So to insert 5, we have to consider this tree as our present tree. So the 3 or 5 can be inserted at this position following the rules of the BST. Now we have a situation where we have to perform a rotation. Okay. So if you calculate the balance factors, so for leaf nodes it is going to be 0, and whereas for 4, so in left side I don't have any child nodes, but in right side I have one child node. So it is going to be 0 minus 1, and for this it is minus 1, and for 3 it is going to be 0, and there are two nodes in the right, so it is 0 minus the deepest child node for 3 is 5, so the number of edges between 5 and 3 is 2, so 0 minus 2 becomes minus 2, and for 2 it is going to be 1 minus the deepest child node is 5, so number of edges in the between 2 and 5 is 3, so it is going to be 1 minus 3, which is minus 2. So now even though two different nodes are having affected balance factors, we should always go upwards, right? We should always go from leaf nodes to root node. Okay, so here if you go from bottom to the top, so the first affected node is this. So first we have to balance this particular subtree and then look into the higher level. Okay, so here if you see, the rotation that is necessary for us is going to be a left rotation. Okay, I believe you already know what left rotation is and why we should perform left rotation. Left rotation is performed when we have inserted a right child to the right subtree. Okay, so here the tree would change into something like this. So 2 stays as it is, and sorry, it is 1. 1 is going to come here, and 3 will be pushed down because we are performing a left rotation between this particular nodes, and 4 goes up, and 5 stays as it is. So now we have performed the rotation operation, right? Here is this, and so 4 goes up, 3 is pushed down, and 5 stays as it is. Now we should calculate the balance factors. 0 for leaf nodes, and for this node it is going to be 0 because left side it is 1 and right side it is 1, and for 2 it is 1 minus the deepest child nodes are this 3 and 5, so the number of edges between them is 2, so it is 1 minus 2, which is minus 1. So now the balance factors are within the range of minus 1, 0 and plus 1, so now we don't have to worry about balancing it anymore, right? Hope you understood how this balancing actually happened, right? Now we can insert the next node. So after inserting 5, it is going to be 6. So we will see how we can insert 6. So first we have to consider this present tree, so which is 2, 1, 4, 3 and 5. right? Now we've been asked to insert 6 to this present tree, and where 6 can be inserted is at this position according to the rules of binary search tree, right? So now we will see after inserting 6 how would the tree change into, right? So first we should calculate the balance factors. 0 for leaf nodes obviously, and for 5 it is going to be -1 because 0 in the left subtree and 1 in the right subtree, and for 4 it is going to be 1 minus 2 which is -1, and for 2 it is going to be 1 minus, and the deepest child node is 6 here. The deepest leaf nodes, right? The deepest leaf nodes are 6 because leaf nodes are 3 and 6, but what is the deepest child node, deepest leaf node? It is 6. So here the number of edges between 2 and 6 is 1 2 3. So here it is -2. So now if you see the tree is imbalanced and the balance factor for this particular node is not within the range. So now what we should do is we should try and balance it. So here it is really important to focus. In order to balance this tree, we should go in the direction where the new node is inserted. So here the new node is inserted in this direction. So the balancing should be made only for this particular subtree. And also remember, in order to perform any rotation, it can be performed only between 3 nodes. So which is the affected node and its child node and its grandchild node. So which is this, okay. And here we should be performing something called a left rotation. And here after performing left rotation, 4 should become the parent node. Now the 4 will become our parent node, and 2 goes to the left side, and 2 is having one left child which is 1, and 4 is having a right child which is 5, and 6 is having a right child, well, like 5 is having a right child which is 6. Now can anyone answer where this 3 should be connected to? Okay, so the question is why we should not keep root node. Root. Keep 3 as root node and rotate. So the question of yours is like in this situation, I believe. So you're asking why we cannot make 3 as root node. So it will not work like that. The reason is, so we should be inserting values into the tree according to the values that is given to us. And it is always important to perform the insertion operation on the finally updated tree. So here to your question, you are asking why can't I make 3 as root node so that 2 and 1 can be pushed down. You can do that, but however here the order has to go like this. So first we have to balance from the lower order to the higher order. So here if you see from this leaf node, if you go upwards, so this particular node is affected first. So we have to balance the balance factor for 3 first here, and then we should perform the rotation to balance this particular node. So it is always that you have to first balance the lower order subtrees and then go to the higher order. Okay. So now to the question. Okay, so Dinesh has answered that 3 has to be inserted to the right side of 2. So this is important because so after we perform rotation operation, we will end up in this situation. So here 4 has to become the root node, and here the 2, which is the parent node of 4, will become the new right child of 4, so which is this node, right? And what about the present right child? Sorry, the present left child. The present left child should be connected to the new left child of 4. So here, so the new left child of 4 is 2. So that 3 is connected to the new left child of 4, which is 2. And the confusion here is where should 3 should be connected? The 3 should be connected to the right side of 2. And the reason is this. So 3 is in the right subtree of 2. 3 is in the right subtree of 2, and that is why 3 must be connected as right child of 2, and this is where we have connected it, right? Now we will see the balance factors. So the balance factors goes like this: 0 for leaf nodes, you don't have to compute them, and for this node it is going to be 0 minus 1, so which is -1, For this it is 0 because 1 minus 1, which is 0. And for this node it is going to be the deepest leaf nodes are 1, 3 in left subtree and 6 in right subtree. So between this and 4, so the number of edges are 2, and 2 minus the number of edges between the deepest leaf node in right subtree 6 is 2. So 2 minus 2 becomes 0. So this is how the balance factors are computed, and here it is 0 in the left subtree and here it is 0 in the left subtree and 2 in the right subtree, it is minus 2, and here it is 2 in the left subtree and 3 in the right subtree, so 2 minus 3 will end up with minus 1. So here the affected nodes with balance factor is 5 if you go from bottom to top, and first we have to perform the rotation between this. Okay, so what rotation we should perform? We should perform a left rotation. Okay, now we will see how the tree gets updated into 4 stays as it is, 6 goes up, and 5 comes down, and 7 stays as it is, and we have 2, 1 and 3 connected as it is. So now the balance factors, I believe, 0 for everything, 0 for leaf nodes, for this it is 1 minus 1, for this it is 1 minus 1, and for this it is 2 minus 2, which is 0. Okay, now the height of the tree is balanced and happy. Now we will insert the next node, which is 16. Okay, so we will insert 16 now. Okay, first we should consider the present tree, which is this tree, 4, 2, 6, 5, 7, 1 and 3. Okay, so now we are asking to insert 16. So where will 16 be inserted? At this position. Okay, now we will compute the balance factors. So the balance factors will go like this: 0 for leaf nodes obviously, and for 16 also 0, and whereas for 7 it is 0 minus 1, which is minus 1, and for 6 it is 1 minus 2, which is minus 1, and for 4 it is 2 minus 3, which is minus 1, and for this it is 0 because 1 minus 1. Now the balance factors are within the range, so this tree is also valid. Now we can insert the next element. After 16 we are inserting 15. Okay, so we will insert 15 now. Okay, so first we will consider the present tree, which is 4, 2, 1, 3, 6, 5, 7 and 16. Okay, now we should compute the balance factors for this tree. So 0 for leaf nodes obviously. Okay, oh, I did not insert 15 yet, my apologies. Let me insert 15 first. So I have to insert 15. 15 will go here. Okay, and the balance factors, 15 gets 0, for this it is 1, for 7 it is minus 2, and for this it is 1 minus 3, which is minus 2, and for 4 it is 2 minus 1, 2, 3, 4, so which is minus 2. Now the balance factor of multiple nodes are affected, so this particular situation is very interesting, right? Now we will see what we can do. So from the bottom, if you see, the first node which is affected with the balance factor is this. So we have to perform what rotation now? Can anyone answer what rotation should we perform in this case? So we should be performing something called a right left rotation. So why right left rotation? Because the balance factor of this node is affected because of we inserting a left child to the right subtree. So that is why we perform a RL rotation. Always remember, RL rotation is performed when the tree structure is like this. Okay, just like this. So first we should perform a right rotation in this situation. which is between the grandchild and the parent node. So which is between 15 and 16. And then we should perform a rotation between these two nodes. Okay. So first right rotation and then a left rotation. So let us perform these steps. Okay. So I am writing them here. So 4 stays as it is, 6 stays as it is, and here 7 also stays as it is, because in RL rotation first rotation should be performed. The right rotation should be performed between grandchild and the parent node. So here, so between 16 and 15 the rotation is performed. So 15 is pushed up and 16 is pushed down. Okay. Now we should not compute the balance factors immediately. We have to perform the next rotation also. So what is the next rotation we should perform, which is left rotation. And now the left rotation is performed between 15 and 7. Now let us go ahead and complete it. 4 stays as it is, 6 stays as it is. Now 15 is pushed up, 7 is pushed down, and 16 stays in the same place. And now 6 is having a node called 5, and 2, 1, and 3. Now this is how the tree is. So first we have performed a right rotation, and then after we perform a left rotation, and this is how the tree is presently looking. Now we will see the balance factors for them. The balance factors for leaf nodes are zeros always, 0, 0, and 0. For this it is going to be 0 because 1 minus 1, and for 6 it is going to be 1 minus 2, which is minus 1, and for 4 it is 2 minus, what is the deepest leaf node, which is 7 or 16. So 1, 2, 3. It is 2 minus 3, which is minus 1. So this is how the balance factors are, and after we complete the right left rotation. Now this tree is looking okay according to the balance factors, and now we will insert the next element, which is 14. Okay, now we will insert 14. So to insert 14, this is what we do. First we consider the present tree, which is 4, 6, 15, 16, 7, 5, 2, 1, 3. Now we have been asked to insert 14. Where will 14 go? To the left side of 15, but left side of 15 already we have 7, and 14 goes to the right side of 7. Now we will compute the balance factors. 0 for leaf nodes, and for this it is going to be minus 1. For this it is going to be 2 minus 1, which is plus 1, and for this it is 1 minus. So what is the balance factor for 6 now in the right subtree? The deepest leaf node is this node, so the number of edges is 1, 2, 3. So 1 minus 3 will be minus 2. And what about 4? So it is 2 minus the deepest leaf node is this, which is 1, 2, 3, 4. So 2 minus 2, which is going to be minus 2. So now because of we inserting 14 here, the balance factor is affected here. So now we should not perform rotation between 15, 7 and 14. We should be performing rotation between the affected node. So the affected node is 6, and we can perform the rotation between 6, 15 and 16. But we should not do it. We should always go in the direction of newly inserted node, which is 14. So the tree that we should consider for the rotation operation is this particular tree. Okay, which is 6, 15 and 7. Now what rotation should be performed? We should be performing a RL rotation again, a right left rotation, because we have inserted 14 to the left subtree of right subtree for 6. So which is 14 is connected to 7, which is left child to the right subtree of 6. So here we should be performing a RL rotation. So first we will perform right rotation between 7 and 15, and then a left rotation between the updated node, which is 7 and 6. So now first we will perform a right rotation. Okay, so the tree is going to look something like this: 4, 6 is going to stay as it is because we are not going to perform first right rotation to that, and the rotation is performed between 7 and 15. So now 7 becomes our root node and 15 is pushed down. 15 is having a right child 16 and 14 is connected to 7, and the new right child for 7 is 15. So 14 should be connected to the new right child of 7, which is 15, and 14 goes to the left side of 15. Okay, 6 is having a child which is 5, and we have 2 and 1 and 3 connected. Okay, now we have completed a right rotation. Now we should perform a left rotation. Now the left rotation is performed between 7 and 6. So we should always keep in mind to which 3 nodes are we performing the rotation. Okay, so the now tree would change into something like this. Okay, so which is 4, 7 becomes our new parent node, 6 is pushed down, 6 is having a left child which is 5, 15 is the right child of 7, and 14 and 16 are the child nodes of 15, and 4 is having a left subtree which is 2, 1 and 3. Now if you calculate the balance factors will be this: 0 for leaf nodes. For 15 it is going to be 0 because 1 minus 1. For 7 it is going to be 2 minus 2. And for 2 it is going to be 1 minus 1. For 4 it is going to be 2 minus the deepest leaf nodes are 5, 14 and 16 in the right subtree. So which is 3 nodes. So which is 2 minus 3, which is minus 1. Now the balance factors are within the range. So now this tree is a balanced AVL tree. So this is how you perform a AVL tree construction for the given list of numbers. I hope all the operations are clear for you. And if you have any questions now, you are free to ask your questions. How 4 is become a root node? So the question is asked from Tendulkar, why 4 is a root node? So why 4 is a root node? Right. So this is the reason, Tendulkar. So 4 has become root node in this step. So after we insert 6, 4 has become root node. So here, so after we insert 6, so which is this particular node. So here after we insert 6, the balance factor for 2 has become minus 2. So we performed a rotation between these 3 nodes because the 6 is inserted in the right subtree of right child. So that is why we have performed a left rotation between 2, 4 and 5. After we perform a left rotation between 2, 4 and 5, 4 has become our root node and 2 is pushed to the left side and 5 is in the right side as it is. And whatever node connected to 4, which is 3, connected to the new left child of 4, which is 2, and this is where we connected it. And from this particular step, we got 4 as our root node, and it just keeps going, right? Yeah. I believe you understood why 4 has become root node. Yes, Tendulkar. And now Dinesh is asking a question. If we have another node for 3, we have, if we have another node for 3, okay. So what do you mean is for this? Which side do you want me to insert, Tendulkar? Okay, I'll first take this tree and then see what can be performed. All right. So now let me just copy this tree and then I can take whatever case you were asking to me. How 4 has become. So the present tree is this. Alright, so now which side do you want me to insert a node, Tendulkar? How 4 is become a root node. I believe you understood how 4 has become a root node. So 4 has become a root node when we inserted 6 into the tree, right? So here if you see, let me just scroll that. So in this step 4 has become root node, and from here on 4 has become a root node, and it just keeps going, right? Yeah. So this step. Okay. Now where do you want me to insert a new value in this present tree, Tendulkar? Where do you want me to insert a new node? I hope this insertion is very clear for everyone, and if you have any doubts, you are free to ask your doubts. Sir, can we check the final AVL? Sir, can we check the final answer by writing tree in order? I cannot say that you can do that, this Mr. BTech. So can we check the final answer by writing tree in order? Uh, I don't think that is possible because we are not very sure which particular value is going to be a root node and which one is going to be a sibling node and all that. I did not try that, to be honest. Maybe it could work, but I never tried that. Writing tree in order, can we get the final answer? That I'm not very aware, but this is how we perform insertion operation. Any questions, guys? Like, or if you are clear with this, then we can move on to the next topic, which is deletion operation, which is even more interesting, to be honest. Any doubts in this, or are you all clear with this topic? Sir, can you please write in order above example? Oh, you are asking me to write in order for this particular tree. Okay, I will do that. So the in order traversal will work like this. First we have to take a left child and then go to the root node and then go to the right child. So the deepest left child here is 1. So I can take 1 and then the root node which is 2 and then the right child which is 3 and then using backtracking I can go back. So which will be 4 and in right side so the deepest left is 5 and then I don't have 6 and then nothing in the right side so it will go back and then 7 and then right which is 14 and 15 and 16. So this is an in order traversal for this particular tree. So this is the in order traversal for this particular tree. I hope everyone is clear with this topic. Shall we move on to the next topic, deletion in AVL tree? Okay, great. All right, I'll just consider this tree itself and we can go ahead and perform some deletion operations, right? So now even for deletion operation also we have to keep in mind that balance factors must be within the allowed range which is -1, 0 and +1 and deletion operation is performed very similar to the binary search tree deletion operation. So where we can delete a child node directly and if we are going to delete a internal node we have to delete that only after swapping the deleting node with the in order successor. Okay, so I believe you all know what in order successor is. Okay, for example let me take this and so that you will understand. So for example in binary search tree it used to work like this. So if I've been asked to delete, okay, if I've been asked to delete 16 here, I can delete it directly because 16 is a leaf node. So I can go ahead and delete 16 directly. Okay. And if I've been asked to, delete 10. So in this case, the in order successor for 10 is nothing. So the in order predecessor is 5. Or it is a situation where we have, only a single child. In this situation, we are going to swap 10 with 5 and then delete it. So what we do is, so we just simply do this. So we get 5 to the top and then 10 to the bottom and then we just simply delete this leaf node which is, so the node which is asked to be deleted. Okay. And now if I've been asked to delete 15, so to delete 15, I have to replace this 15 with the in order successor which is this. Okay. So now the tree would change into something like this. So 16 goes up and 5 stays as it is. So this is how binary search tree deletion operation actually works. So we can delete a child node directly and if it has a single child then we can swap that single child with parent and delete it. And if we have more than one child nodes, that is when we have to replace the node to be deleted with in order successor and then delete that node which to be deleted after getting that to the leaf node position. So added to this, so far we have seen how binary search tree deletion used to work, but now we should understand what should we do to balance the balance factors. Okay, so to balance the balance factors, you have to perform the rotations. For example, if I've been asked to delete let us say I have tree like this. Okay, so now if you find the balance factors for this, so 0 for leaf nodes and 1 for this and 2 minus 1 which is 1. Okay, now if I've been asked to delete 20, since 20 is a leaf node, I can directly delete it because 20 is a leaf node, right? But now we should see what happens to the balance factor. So the balance factor of this node has become 2, which is not the valid balance factor in the AVL tree. So now what we should do, we should perform a rotation in this particular tree to balance the balance factor similarly. So here we are going to perform a right rotation, and in this case 7 becomes our root node, 15 becomes our right child, and 3 stays in the left child position. Now the balance factors are within the range. So this is how we are going to perform a deletion operation in AVL tree, right? So this is how we perform the deletion in AVL tree. Hope you understood the basics before we get into the AVL tree deletion problem. Now we will see how we can solve this problem. Okay. Now can anyone give me the list of numbers which I should be deleting from this, or can I just take them on my own? Any numbers, or can I just take them? Can you give me any list of numbers, guys? Okay, so I've been given with numbers. So I've been asked to delete 7, then 2, then 4, and then 15. Okay, so now we will see how we can delete 7. We will delete 7. Okay, so we will delete 7 now. So where exactly 7 is at? 7 is at this position, and 7 is not a child node. So 7 is a internal node now, so which is having more than one child nodes. So now what should we do? We have to replace this with the in order successor. So in order successor is not that very complicated to understand. It is just nothing but the biggest number in the right child or the right subtree. So in the right subtree, the biggest number is what? Sorry, in the right subtree, not the biggest number. It is the smallest number. My apologies. So the smallest number in the right subtree. So the smallest number in the right subtree is what? 14. So now I have to replace 7 with 14 and then delete it. Okay. So how would the tree change into? The tree would change into something like this. 4, 14 goes up and 15 stays in the same place. 16 stays in the same place. 6. Okay. And now what about 6? So it is going to be 1 minus 0, which is 1. And for 15 it is 0 minus 1, which is minus 1. For 14 it is 2 minus 2, which is 0. And for 4 it is going to be 2 minus 3, which is minus 1. And for this it is 1 minus 1, which is 0. Okay, so I've been asked to explain performance analysis, speed and time complexity. I'll explain them too, but let me complete this deletion operation. All right. Okay, so I've been asked to delete 7. Hope you understood how we have deleted 7. Now we will delete the next number, so which is 2. So the present tree is this. Now we have to delete 2 from it. So we are asked to delete 2 from it. Now we will delete it. So where is 2 at? 2 is at this position, okay, and 2 is an internal node again, which is having more than one child nodes. Now we have to again swap that with the in-order successor. So the in-order successor is the smallest number in the right subtree, which is 3. Okay, so now we will make 3 as our parent node in place of 2, and 1 stays as it is. 14, 6, 5, 15, and 16. Now we will calculate the balance factors. 0 for leaf nodes, and for this it is -1, and for this it is +1, for this it is 0, and for this it is 1, and for 4 it is 2 minus 3, same as it is -1. So we have deleted 2 also successfully. Now we should delete the next number, which is 4. So we will delete 4 now. Okay, so where is 4 at? 4 is the root node, so which is having multiple child nodes. Now we have to swap 4 with the in-order successor. So the in-order successor for this 4 is 5. So the smallest element in the right subtree, which is 5. So we have to swap 4 with 5. So now 5 gets to the position of 4, and the remaining node stays in the same place. 6, 15, and then 16. Now we will calculate the balance factors. So 0 for leaf nodes, alright, and for this it is 0 minus 1, for this it is 1 minus 2, which is -1, and for this it is 1, and for 5 it is 2 minus the deepest child node is 3, which is 1, 2, 3. So 2 minus 3 is -1. Now the balance factors are again within the same allowed range. Now the last element which is to be deleted is 15. Delete 15. Okay, now I'll delete 15. Where is 15 at? 15 is the parent node, which is having only a single child. So we'll swap 15 with 16 and delete it. So we'll write the updated tree. 14, 16 comes to the position of 15, 6, 3, and 1. So calculate the balance factors now. 0, 1 for this, 2 minus 2, 0 for this, 0 for this, 0 for this. So this is disappointing because I expected some rotation operations in this, but unfortunately we ended up with the balance factors which is within the range, so which is not a win-win situation for us. All right. Do not worry guys, if you would like to see different situations in AVL tree for deletion operation, I already made a video for that, AVL tree deletion operation, wherein you will end up with all the possible situations, like after deleting you will end up with right rotation, sometimes you will end up with left rotation, sometimes you will end up with right left rotation and left right rotation. And I have came up with a example problem which includes all the rotations in such a way that all the rotations are included after performing the deletion operations. If you have missed watching that video, do watch that video. It is really beneficiary for you to understand because all the rotations are included in it. This example is not giving us any rotations. Okay, we've been asked to delete 14 from Gayatri. Alright Gayatri, we will delete 14 from here. Even after deleting 14, we will not end up in rotations, Gayatri. We will see that, okay. So 14 is a parent node which is having two child nodes. So in-order successor should be replaced here, which is 16, okay, the smallest number in the right subtree. So now 5 stays as it is, and in place of 14, 16 comes up, 6 comes here, 14 is deleted, and then 3, and then 1. Okay, now the balance factors are what? 0 for leaf nodes, 1 for this, 1 for this, and 0 for this. Again, same. Okay. Any other nodes to be deleted, guys? Alright, so now I think I can get into some situation here. Maybe if we delete, maybe I'm not very sure, but maybe if we delete, let us say if being asked to delete Uh, 5, 5 now. Let us see after deletion of 5 what happens. 5 is a root node and I have to swap that with the internal, sorry, in order successor, which is 6. So 6 goes up, 16 stays here, 3 and 1. So balance factors 0, 0, 1, and for this it is 2 minus 1, which is 1. Now let me delete 16. Delete 16 maybe. I'm not very sure. Yeah, 16. After deleting 16, 6 stays there, 3 and 1. So balance factors are 0, 1 and 2. Now we have a rotation operation required. So here the balance factor is affected for this particular node and we have to perform a right rotation. Okay. And after right rotation, the tree would change into this. So 3 becomes the root node, 6 goes right child and 1 goes left child. Now the balance factors are 0, 0, 0. This is a perfect AVL tree. I hope you have understood the deletion operation. Sorry, we did not get into much of rotation operations. I expected all the rotations possible in this example. If you want to watch such type of example problem, do watch the video which I have uploaded in my channel, AVL tree deletion operations. That has all the rotations involved in it and different situations. Just watch that video, you will understand deletion operation very clearly. All right. Any other doubts? Any other questions, guys? If you have any questions, then I'll just explain them. Search operation in AVL tree works similar to binary search tree search operation. It is nothing different. I believe you already know how the search operation works in binary search tree. For example, if I've been asked to search 14 here, okay, so it is going to work like this. First comparison is made between the root node and the element to be searched, which is 14 and 4. 14 is bigger than 4, so I have to check in the right child, which is 7. And again 14 and 7 are compared. Again 14 is bigger, it is going to go to the right child. And now 14 is compared with the right child of 7, which is 15. And now 14 is smaller than, sorry, so 14 is smaller than 15. So since it is smaller than 15, so it is going to check in the left child. So 14 and 14 is compared, they are very same. So now we will say that it is found. Okay, so this is how search operation works in AVL tree. It is very similar to binary search tree, nothing different. All these steps are very same. I hope you have understood how this AVL tree operations works, guys. Uh, do subscribe to this channel. You know, I have made so many videos on the data structures. I will be uploading many videos on data structures and different programming languages. And you can also request me in comment section, or you can, you know, ask me, not request, you can ask me to make any of the videos or live sessions like this on any of the topics that you want me to make a live session on, so that I'll be very happy to make use of the time and give you the better explanation on different examples. Right, Tarun has asked me to construct an AVL tree for this example problem. If you want me to make it, I can make it now, Tarun. The example that is asked by Tarun is this. So he's asked me to construct an AVL tree for this numbers. And if you want me to construct it now, I can, because this particular live stream is going for more than 1.5 hours. If you want me to construct an AVL tree for this, and if you are willing to continue in this, you know, live stream, then I can help you in understanding this example too. You want me to make a video on this now? Like, do you want me to explain this now, guys? Can you make a video on time and space complexity? I'll make a video on time and space complexity, guys. uh, I'll get that video uploaded by end of tomorrow at any cost. I've been thinking to make a video on space and time complexity, which is the first unit topic in advanced data structures and algorithms. I will record a video and I'll upload that by end of tomorrow. I'm also going to upload a deletion operation in B tree as well. Even that will be available tomorrow. I've recorded it, but I did not upload that video yet, and I will be uploading that tomorrow. Okay. Do you want me to solve this problem now? Constructing an AVL tree for this problem? Okay, I got one yes from Uma Devi asking to construct an AVL tree for this problem. Any other yeses, guys? No, sir. Instead of that, you may explain other any important topic. What topic do you want me to explain now? It is Venom Striker. Venom Striker, such a nice name, boy. Okay, then let me just quickly complete this and then just get into the next topic if you want me to, or we'll just wind up this live session now. Okay, so no, sir. Yeah, so I believe they are okay uh with this. Right, Tarun, it is yours now. Like, if you ask me to go ahead and construct, sir, explain the topic in unit 1. All right, Asma. Do you want me to do it now, or maybe in next live stream session, or now it is fine? Right, guys, then I'll just get into this so-called asymptotic notations, which is really important. And before we get into asymptotic notations, we will see what exactly time and space complexities are. Okay, so first I'll explain what time complexity is, and then what is space complexity. Okay, so time complexity can be defined like this. So it is the amount of time which is taken by an algorithm to complete its execution. All right. So for example, if you take this, so if you take an array of size this, so maybe say we have an array of size like this, 0 1 2 3 4 5 6. So the total number of values that we have here is 7, and okay, so if you name this array as A, so here in order to check whether a number is present in this particular array or not, so the amount of time that it has taken to search that given value can be said as time complexity. So since we cannot imagine the amount of time it is going to take, like in seconds or microseconds or milliseconds, we understand time complexity like this in this particular example problem. All right, so here I can believe that the time that is calculated as in terms of comparisons. Okay, so here let us say in worst case or best case or average case. So in worst case, let us say I have been asked to search for 70, which is the last element in the array. So how many comparisons are we going to make here? 7. Okay, so if you imagine each comparison it is going to take 1 second, then the total amount of time that we ended up taking is 7 seconds. Okay, 7 seconds. So this is what the worst case, right? And then we have something called best case. So best case can be defined like this. So the value that you are about to search is found in the very first step. So for example, if I've been asked to find 10, now 10 is found in the very first step or very first comparison. And what is the number of comparisons that we have taken? Only one. So if you take one comparison takes 1 second, then it is going to be only 1 second. So this we call as best case time complexity. And what about the average case? Average case is the average amount of time that it is going to take in order to find an element. For example, if I've been asked to find 30 here, so what is the amount of comparison that you are going to perform? 3. So what is the size of the array? Which is 7. So the average time complexity for this problem is 3 seconds. So this is what time complexity is. Time complexity is nothing but the amount of time that it is going to take to complete the execution of a given algorithm or to complete the execution of a given program. So that we call as time complexity. Okay, and to this time complexities are of not just one case, it is of 3 different cases. And what those cases are: the best case, and then the average case, and then the worst case. Okay, so best case is something that which the value which you are about to search is found in the very first step. So it is like the very least amount of time that it is going to take in order to complete the execution of a given problem. So it is nothing but the least time. Okay, and average case is like the average amount of time that it is going to take. And the last one is worst case. It is the maximum amount of time that it is going to take in order to complete the execution of the given problem. So the first case is best case, the second case is average case, and the third case is worst case. So best case is the least amount of time that it takes. Average case is the average amount of time that it is going to take to complete the execution of the algorithm or program. And worst case is the maximum amount of time that it is going to take to complete the execution of the given problem. Okay. So happy that Tarun has acknowledged, saying, I'll try for that number, sir. Now I have understood. Awesome, Tarun. Keep that confidence, all right? Right. I believe you have understood what time complexity is. Time complexity is the amount of time that it is going to take in order to complete the execution of the given algorithm. All right. Now we will see what space complexity is. Okay. So space complexity is nothing but the amount of memory that it is going to take to complete the execution of a algorithm or program. So it is something to do with the memory. So for example, here in this case, I was asked to check whether a given number is within the array or not. So for this, if you take the amount of space it is going to take. So let us try writing the pseudo code for this, and then we can understand. All right. So let us say we need the searching element. So search, let us say I have taken 70, and then now I need to start a for loop for I, or maybe I can do it like this. For I equals to 0 to n, do if search equals to array of I, then we can say that found. Okay, so here if you take the amount of space that it is going to take is, first we have to compute the constant time. So constant time is what? Sorry, constant space. So this particular variables, it is not going to change. I mean, like the amount of space that it is going to occupy is very same. So here we have the constant variables, what? Search variable and I variable. So we have two variables who is going to take the same amount of space. It will not change in respect to the size of the array. So here we have 2 plus. So whatever the size of the array is represented in terms of n. So here the space that it is going to occupy is 2 plus n, right? And this is the amount of space that this particular algorithm is going to take to complete its execution. So this is how we compute space complexity. Space is nothing but the amount of memory it is going to occupy in order to complete the execution of this particular problem or algorithm. Okay. So even for space complexity also we have three different cases. So the first is best case, and then average case, and then lastly worst case. Okay. So it is very similar to the time complexity cases, which is best case time complexity, average case time complexity, and worst case time complexity. For space complexity also we have best case, average case, and worst case. Right. So best case is the least amount of space that it is going to take to complete the execution of the program, and average case is the average amount of space it is going to occupy, and worst case is the maximum amount of space that is needed in the memory to complete the execution of that particular program. So this is what the time complexity and space complexity actually mean, and it is always important to remember that we have, okay, I'll explain that later after I explain the asymptotic notations. But before we get into asymptotic notations, I believe you have understood what time complexity is and what space complexity is. And if you have any questions, then I will answer your questions, and then we can move on with the asymptotic notations. Any questions on this, guys? If you have any questions on time and space complexity, then I'll clear them before we dive into the asymptotic notations. Not getting any comments from you guys. Sir, can you give an example? Oh, can you give example of complexity based on trees? Complexity based on trees? Okay, so as I said already, when I have explained about the benefits of AVL tree, right? So it is just told that the binary search tree takes a time complexity of big O of n in worst case scenario, and AVL tree or splay tree or B tree and all these trees are balanced trees which takes a time complexity of big O of log n, right? What we actually mean by that is that, so in binary search tree the time always depends on the number of nodes in the tree. In worst case scenario, I'm not talking about the best case, in worst case scenario. So worst case scenario can be represented in trees like this, which is nothing but a skewed tree. Okay, so if you take 5, 10 and 20. Okay, so here it has 3 nodes and we are going to take 3 in the worst case search time. For example, if 20 is asked to be searched, we take 3 number of comparisons here, which is like 3 seconds if you take one comparison like 1 second. But whereas in AVL tree, this tree is not allowed. So what we do, we rotate it and so that it can be balanced. So the tree would look something like this. So here, even in the worst case, if someone is asking you to check or search 20, so the number of comparisons that we are going to end up with 2, right? So which is nothing but big O of log n. So why it is said as big O of log n? Because so the height of a tree can be represented as log n, which is nothing but height of a tree, right? So here the height of a tree is what? 2. So in worst case scenario, so the number of comparisons that we are going to end up in a balanced tree is 2. So this is where we try and compare the time complexities in binary search trees and AVL trees. I believe I have answered your question, Mr. BTech. Shall we go with asymptotic notations? Okay, so the asymptotic notations are going to go like this. So asymptotic notations are nothing but the expressions which are used to represent the time complexity in all the 3 different cases for any given algorithm. So asymptotic notations are used to represent the time complexity and space complexity of an algorithm. So asymptotic notations are of these many types. So the first and most famous asymptotic notations is big O notation. Okay. And then the next asymptotic notation that is more popular is that omega notation. Okay. And the third one is theta notation. Right. So these are the more popular notations in asymptotic notations, which are used to represent the time complexity of any given algorithm. Not only time complexity, it can be a space complexity also. Okay. Now we are going to go with a big O notation. And big O notation is used to represent the time complexity of a problem, and in which case, in worst case. Okay. Now big O notation is used to represent time complexity of an algorithm in a worst case scenario, or it is used to represent the worst case time complexity or space complexity of an algorithm. For example, before I said that the time complexity of a binary search tree is big O of n. So we use big O notation for representing the time complexity or space complexity of any given algorithm in data structures. Why big O? Because so worst case is the more uh, safest way of telling the complexities for any given algorithm, because that will always tell to users that it is the maximum amount of time it is going to take. So if any problem is solved before the maximum amount of time that we have quoted, then the user is going to be happy and he will not be disappointed with our algorithm and our promises will be kept as it is. So for example, if I say that this algorithm is going to take 15 seconds, and if the algorithm in execution has taken only 10 seconds, the user will be very happy that it has taken only 10 seconds, whereas I have quoted them 15 seconds. But let us say I have told him that it is going to take only 5 seconds to execute or complete, but it has taken 10 seconds now. Now the user will not be happy with the way it executed because it has taken more than the quoted time. And that is why in data structures we always give worst case time complexity or space complexity for notating the complexity of an algorithm. Now we will understand what big O notation is. Big O notation is used to represent the worst case time complexity. Okay, there is a question how to find time and space complexity. Okay, explain with example. All right, I'll explain how to find time and space complexity with example. But before to that, let me complete this and then we can get back into the example of how you can find the time and space complexity for any given algorithm. Okay. So big O notation is used to represent the worst case time complexity or space complexity. And the equation for big O notation goes like this. So which is big O of n big O of g of n is always less than or equals to f of n. Okay. So the equation goes like this, and the corresponding graph for this would look something like this. Okay. So if you believe that this is f of n, okay, and this is g of n, which is nothing but there will be a constant called c into g of n, right? Now this you can assume as n, which is the size of the problem, and this as time. Okay, this graph explains how big O notation actually works. All right. So if you feel that f of n is nothing but the real time, the the reality time that it is going to take to complete the execution of a problem, so which is this. So if you believe that it is like say 5 seconds or 10 seconds or whatever, and the big O of n, so the worst case time complexity will always be a higher bound or upper bound to the reality time. So for example, we will be quoting as 15 seconds. Okay. Now we tell that in worst case scenario, for example, if I tell to a person that it is going to take 15 seconds maximum, then 15 seconds maximum is represented like this. And any time that algorithm is executed, it is going to take less than 15 seconds every single time, and that we call as big O notation. So big O notation tells that it will always have a upper bound to the reality time that it has. So the reality time that it has is f of n, which we take an example like 5 seconds, and the big O notation, the maximum amount of time it is going to take is 15 seconds. Now this is how we represent the big O notation, and the equation is also trying to tell the same. So I told you that f of n is the reality time that it is going to take, and I told you that it is always less than the big O of time complexity, which is big O of g of n, right? So this can also be represented like this. So big O of g of n can be represented as c into g of n, which is always less than f of n. Okay. So c into g of n is nothing but a constant of c. So which is nothing but the difference between the reality time and uh, the reality time and the maximum time that it is going to take. So here, for example, if you take the constant is nothing but it can be 3 or it can be 2 or it can be anything. So in this example, it is going to be 3. So it is nothing but c into g of n less than or equals to f of n, right? So this is how you represent the time to the reality time, which is f of n. So this is big O notation, and big O notation is always used to represent the worst case time complexity situations. Okay. Now we will see what omega notation is, and omega notation is opposite to the big O notation. Okay. So it is greater than or equals to f of n. I'm sorry, so I have written same here. Oh, my apologies, guys. It is represented in opposite. So it is represented in opposite. So big O of g of n is always bigger than f of n. So here if you see f of n is smaller than big O of g of n. So big O of g of n is always bigger than the f of n, the reality time. It is always like it is going to take more time than the reality time. As I said, the worst case scenario is going to take big O of n. So it is always bigger than the reality time. I said that it is the best case scenario, right? Let me just complete writing it. So big O of, sorry, omega of g of n is always less than the f of n. So the corresponding graph would look something like this. So this is size of the problem and this is the time. So it is that the omega notation is used to represent the best case situation. So the graph will always be in the lower bound. To the is always in the lower bound of the reality time. So for example, if I, in order to represent the omega notation in our example, let us say it is going to take 5 seconds to complete the execution of the problem, and I always quote to the user telling that it will take only 2 seconds or 1 second f of n. So that means, so omega notation representation. Now we will discuss about theta notation. Theta notation can be represented like this. It is used to represent something called average case notation. So it is going to use two bounds because it is average case time complexity representation. So the graph would look something like this. So it is going to take a lesser bound one. If you imagine like c into g of c1 into g of n, and if you think that this is the reality time f of n, and we have something called a upper bound which is c2 into g of n. Okay, so now this is for big O notation and this is for omega notation, and this both combined gives us the theta notation. Okay, so this can be represented like this. Okay, this can be represented like c1 into g of n is always less than or equals to the reality time which is f of n, and f of n is always less than or equals to c2 into g of n. So which is nothing but omega of g of n is less than or equals to f of n, and it is less than or equals to big O of g of n. So this is how you represent a theta notation, and theta notation is used to represent the average case time complexity in a given problem or for any given algorithm. Right? Hope you understood what asymptotic notations are. So asymptotic notations are used to represent the time complexities. Big O notation is used to represent the worst case time complexity, and it believes that its time complexity is always higher than the reality time which is f of n. And omega notation is used to represent the best case time complexity, and it tells that it is always less than the f of n or the reality time. And the last notation is theta notation, which is used to represent both lower bound and the upper bound time complexities, and that is why we make use of two different time complexities here. Hope you understood asymptotic notations, and if you have any questions in this, you can mention them in the chat. All right, now we will see how we can calculate the time and space complexity for any given algorithm. All right. Okay, so now if you see, like I'll try taking an example algorithm first, and then we can see how we can calculate the time and space complexity for that. So here I will take this algorithm for an example. All right, so for an example, let us say I have a swap function who is taking two arguments as input. Here let us say I have like x equals to a, which is a temporary variable, then I will take a equals to b, and then I will take b equals to x. So now this is the swap algorithm which will swap two given numbers and they will just change them one into the other. Okay, now to calculate the space complexity, let us first calculate the space complexity. So here space complexity is nothing but the amount of memory it is going to occupy. So here we are not going to think about the number of bytes it is going to occupy. Here we can represent them as in like a number of units. Okay, so here how many variables do we have? So we have 1, 2 and 3. So what is the how many number of units that we are going to make use? Here in memory we are going to make use of 3 units of space. So here we are going to make use of something called 3 units of space. So here the space complexity is 3. Okay, now if you try and see how we can perform like sum of n given numbers, we will see how we can perform sum of n given numbers. So here let me take a different algorithm now. Okay, so I'll write the algorithm here. So maybe say I have an algorithm called sum of all, which will take the size of the array, and also it will take something called array as input. Okay, now we have to make use of something called a for loop, and we need one more variable called result. Maybe I'll take 0 initially. So then for I equals to 0 to size of the array. Now how do you compute the sum of all the numbers? So it is very simple. Result equals to result plus a of I. Now this particular algorithm is used to find the sum of n given numbers in an array. Okay, now if you see the space complexity, it changes. Okay, so if you see first, how many variables are we going to make use? We are going to make use of 1 and 2 and 3, so which is the constant space which is required, doesn't matter the size of the array. So we need 3 initially, and then we also need the number of elements that we pass in as input or size of the array. So for example, if I give 10 numbers, I have to allocate memory for 10 different numbers in the array, and if I give 20 numbers, I have to allocate memory for 20 numbers. Now it is depending on something called size of the array, and that we can represent as n. So now the space that is required to execute this particular algorithm is n plus 3 or 3 plus n. So this is how we represent the space complexity or compute the space complexity for any given algorithm. Okay, I've been asked to explain little o and little omega notation. I'll explain that also, Tendulkar. Let me just finish this first, okay? Hope you have understood how you compute the space complexity. Now we will see how we can compute the time complexity. Okay, now we will see how we can compute the time complexity. Okay, so time complexity is nothing but the amount of time that it is going to take. So here, if you take 1 unit for every single line that it executes, how many lines do we have here? We have something called 3 lines. So it is going to take 3 units of time to complete the execution of this particular algorithm. All right, and we will see how we can compute the time complexity for this. So here if you see, so for this line we need 1 unit, and for this also we need 1 unit. But what about this for loop? It will be executed for n number of times, and this for loop is going to get executed according to the size of the array, and we represent that as n, right? So which is 1 plus n. And not only that, this for loop also takes one extra iteration to check the failing condition. For example, if I have to execute or find the sum of 10 numbers, so this for loop will be executed for 10 times, and also it will execute for the 11th time to check the false condition, so which is like 10 plus 1. So here it will be n plus 1. So in total, the time complexity required for this algorithm will be n plus 2. The time complexity for this particular algorithm is n plus 2. Okay. Hope you understood how to find the time complexity and space complexity for any given algorithm. And let me just show you where we will end up with squared time complexity. So for example, let us say I have to iterate through a matrix. So how do you iterate through matrix? For I equals to 0, I less than or equals to n, and I plus plus. And for columns, I need to again iterate through for j equals to 0, j less than n or m or whatever it is, j plus plus, and we will just write some statements here. All right. So here we will be getting into something called squared of n. So because for every given, for example, there are 3 rows here and 2 columns here. So the total number of times this for loop is going to get executed is 3 times for the rows, if we have 3 rows, and every row there are 2 columns, so it is multiplied with 2. So it is going to be 6 times. So this can be represented in time complexity as n square time complexity, or n square plus 2. N square plus 2. So this is how we represent this. So which is nothing but n plus 1 times for this, and n plus 1 times n times for this, and n plus 1 into 1 plus 1 will become n square plus 2 or whatever it is. All right. So this is how you represent time complexity for a nested loop. And what would happen if I had one more loop inside this? Would it still be n square or would it be n cube? Not getting any answers, guys. Okay, so it is n cube it is, because we will have 3 loops inside it, like one loop inside one loop, and then we'll have one more loop in it. So it will be n into n into n. So we will end up with n cube. All right. So that is how we compute time complexity and space complexity. And if you have any questions on this, I will explain them, or I can just dive into something called the 2 other notations, which is little o and little omega notation. Okay. Hope you have understood big O, theta and omega notation. Now we will see what is little o notation. Okay. So what exactly the difference between little o and big O notation is this. So little o and big O represent the upper bound itself, but Is it representing loose upper bound or tight upper bound? That exactly where the answer lies between the little o and big O. So here if you see the graph of big O notation, so this particular bound which we call as upper bound, it is a loose upper bound, oh sorry, a tight upper bound. That means there is no that big difference between this particular curve and this particular curve. So big O notation is used to represent a loose upper bound, representation. Okay, but whereas in little o notation, we use this to represent a tight upper bound, sorry, a loose upper bound one. Oh, why am I confusing myself? Big O notation is used to represent something called tight upper bound, because here if you see the curves are almost similar, right? But there is only a upper bound of little. But whereas in little o notation, it is used to represent something called a loose upper bound. So the graph for this little o notation would look something like this. If you believe this as f of n, and it is going to be something like this, which can reach up something like infinity. Okay, so this type of representation we call as little o notation. Okay, now little o notation is used to represent worst case itself, but what type of worst case are the curve that it is going to do us? A loose upper bound curve, sorry, a loose upper bound curve is going to do or represent a loose upper bound curve, and that representation we call as a little o representation. And the last one is little omega notation. Okay, similar to little o notation, it is also used to represent a loose lower bound. Okay, it is going to be used to represent a loose upper bound representation. Okay, so the graph would look something like this for this. So if you take this as f of n, and the omega notation would look something like this, it would go to negative infinity, right? So this is how the little omega representation is used to represent. So this is also used to represent the best case, but what type of curve it uses? It uses something called a loose lower bound representation. That means it will be very downward, and it will not be very much closer to the reality time. So this is the difference between big O and little o. Big O representation is used to represent the tight upper bound representation, and whereas little o is used to represent the loose upper bound representation. And omega representation is used to represent the tight lower bound, but whereas little omega notation is used to represent the loose lower bound representation. Hope you have understood little omega and little o representations. Hope you have understood the time and space complexity and also asymptotic notations. And if you have any doubts in them, you're free to ask your questions. I hope we can wind up this live session, and it is happening for more than 3 hours. Any questions, guys? Right, guys, I think it is already late. We should go have our lunch. If you have any doubts and if you want me to cover any other topics, and if you have doubts in today's topic which we have covered in this live session also, do mention that in the comment section so that I'll record a video and upload that in the channel. And if you have not subscribed to the channel yet, do subscribe to the channel, and do share these videos with your friends who are having difficulty in understanding data structures better, so that they may get benefited with this. Right, everyone, thank you for joining this live session. I believe